Good evening. So I had to connect my iPad again with my laptop, and there was some delay due to that problem. So today what I wanted to do, what I didn't get to do this week, was to do a review of the units. So I did all the remedial. You have a test that I've posted, and now I just want to go through the highlights of the chapters. And that test is due tomorrow at midnight. If you have any issues or questions about it, please let me know. I think some people have already finished it. As I sent in the email today, you can attempt it as many times as you like, but I think only after the first attempt will you see your score. So we won't see which ones you got wrong or right. At least that's what I understood when I set it up. Okay, so are there any questions? Hi, Manuel. So I wanted to go back to chapter 2, and then when it comes up, I will get into the calculus with the applications in economics, and I'll get into the statistics with the applications in economics as well, okay? So you'll see them. So we left off talking here in chapter 2 about consumer surplus and producer surplus. And the diagram we could begin looking at what that is, considering the person or the consumers right here. So these consumers, the quantity demanded is 0 at this price. Okay, at this price, the quantity demanded is 0. Now if the price goes down a bit, there's consumers, or there's demand that's a little bit more, right? Positive demand. And you can see we already talked about the downward sloping demand curve. The lower the price induces or invites more consumers or more demand overall, okay? So the quantity demanded goes up. Consumer surplus considers the demand curve and the price at equilibrium. You see here, this is the equilibrium price. This is where the market clears. At this price, for 800 units of quantity of the good, 800 units at this price would be sold. However, the consumers or the goods demanded, where consumers were willing to pay more, experience an economic benefit, which we call the consumer surplus as a whole. So for these individuals, you know, for someone or these items that were priced much higher, the willingness to pay for these units was a price much higher than what was settled. So this creates for these units what we call consumer surplus. And then what we consider are all the units before the 800th unit. Okay? And so this pink area as a total, the area as a total is considered to be consumer surplus. Similarly, at this price, no supply is provided. But at a higher price, suppliers can be induced to produce. Okay, so you see quantity demanded increases from there all the way to the equilibrium price. Now there, for all these units before, suppliers were willing to supply at a lower price, but they benefit for each of those units as a whole. There's a benefit that's known as the producer surplus. Okay, and together, these amounts are known as social surplus. So consumer surplus is the difference between the economic value of a good or its demand price and the market price the consumer must pay. The producer surplus for each unit supplied, the difference between market price and the minimum price producers would accept to supply the unit, that's known as producer surplus. And social surplus is the sum of the two. So it's the area below demand and above supply. Now we use this to examine the impact of out of equilibrium scenarios. Okay, so this is that's what economists refer to. So it all makes sense. It's all pretty and perfect when you look at it here, and it does make sense unless you have any questions. Okay. All right, Manuel's asking about the high. It would be the highest or the last. I guess I think I get to pick. I see all your attempts. But yeah, no, I would pick the highest one. I'm thinking now, I can't remember, but I think I see all your attempts and I would pick the highest attempt. So if you mess up on an attempt, it'll pick the highest one. Okay. Okay, so we speak about equilibrium and then adjustments to equilibrium as a result of changes, shocks impacting supply and demand curves. And we talked about variables that could do such a thing as shifting either the demand or supply curve. And what we would want to do, either anticipating those changes, like we anticipate new customers for a product through advertising, let's say, and we want to see, well, if we have more customers, what can we predict will be the demand for that product? So we could do qualitative forecast where we just predict the direction, what we can anticipate. And sometimes you can actually say what we can expect if we just expect one change in either supply or demand. But if there's a cascade of changes, we might not be even able to predict what qualitatively will happen in the end. Does the price goes up? Does the quantity go down? We might not be able to say that. You might be more ambitious even. You want a quantitative forecast so you can predict both the direction and the magnitude of the change. So you can actually make a prediction about, how much will demand change by as a result of some shock. Okay, so we got to be careful. In clarifying if we're talking about shifts or moves along the demand or supply curve. So we talked about shifts. So this, let's see. I think we looked at these curves. What could happen? Sorry, I'm flipping through the slides. So we did discuss this. So at each price, supply increases because, let's say, there's an improvement in technology that makes it possible for higher production, greater production. So at each price level, there's an increase in supply, and so you could connect all the dots as a parallel shift forward in that case. And what is the effect of that? As a result, if more can be supplied, so we have this new supply curve. If this was the equilibrium price, and this much was supplied, but at that high price, only this much was demanded. To induce consumers to purchase, it might actively lower the price, right? And then that will bring consumers into the market. They're willing to buy more, the ones who are already in the market. And so you would see suppliers, maybe even more suppliers, or suppliers already providing would like to provide even more at a lower price. And so that removes this excess supply. So there's a shift initially, and then there's an adjustment along the demand curve to bring us to the new equilibrium price. Okay, so that's just with a supply shock, and we could look at it similarly going back. A supply shock that reduces supply. Okay, so let's say there's a new regulation that makes it more expensive to produce. At every price, we're going to reduce supply, and that creates a shift backwards. In this case, at this price, consumers at this price would demand A, to this is effectively where suppliers at this price will produce this amount here. to induce suppliers to provide more, consumers would be willing to bid up the price to get more, and that will result in this readjustment to this new price. This would be the new equilibrium price. Okay, let's see. So what if both demand and supply shift at the same time? So I talked about here a supply shift where demand stays constant. You could do the same when, similar, I could look at a demand shift where the supply stays constant. Okay, so we can just look at static shifts. But there could be simultaneous shifts. More dynamic would be if there was a supply shift that then created a cascade of effect on demand. So let's say well, let's look at the examples that we have here. So the question is, can we predict either the direction in which the price changes or the direction in which quantity changes, but not both? Sometimes it's indeterminate. Sometimes you can't say for sure. If both demand and supply increased, we could say that quantity will rise, right? So these are both going forward. Let's look first. Demand increased because of any of the variables that we considered. If this is, let's say this is the demand for, so originally here, this is our demand curve, and this is the demand for beans. And the price of rice drops, and beans and rice are consumed together. It's possible then that there'll just be an increase in demand for beans as a complementary good at every single price. So we can talk about that shift. So that's just an example. And then let's say at the same time, so these are, remember, these are things that are, the effects of the shock are from variables that are not either the price itself or the quantity demanded itself. Let's say at the same time there was some sort of improvement in the manufacturing process or the production process of the beans, and it made supply increase for at every price. So you have these two shifts. We're going to go from where we started, the original demand and supply, A, and that will take us to the new one up here. Now, if supply only increased this much, the price actually went up and the quantity demanded increased. If the supply went even higher, it's indeterminate if the price actually went down, but the quantity demanded still increased. So what is this saying? depending on the strength of the supply shift, price might rise or fall, but quantity for sure rises. So I don't expect you to memorize any of these. You could draw these each time to get a feel for it, but I'm trying to think of an example that can help you memorize that, but you don't have to memorize. There's no need to memorize that. Okay? So if you have simultaneous shifts, you can be sure that quantity increase, if they're both increases, so demand goes up and supply goes up, quantity demanded will increase. But the price, you're not sure if it will rise or fall. It depends on the strength of the shifts, the relative strengths of the shifts. Now here, what's indeterminate? If demand falls but supply increases, you can be sure that price will fall, but it's indeterminate if quantity will rise or fall. All right? In this case, if it's the reverse, so demand increases for a product, but supply decreases, this will force the price to rise. So there's less supply, think about it, and higher demand. To clear the market, the price will have to rise. It's indeterminate, though, if you have more or less of the product. Okay? So these are some results. If both demand and supply drop, you can be sure that quantity falls, but it's indeterminate if the price will rise or fall. So these, you can think about different scenarios, and I think the text offers some examples, but you can also think about this. There's some exercises that get you to practice that. But this is when people talk about it's just demand and supply. These are not it's not a given that if, you know, as just when one of supply and demand is affected, you know what happens, but if they simultaneously are affected by shocks, then you might not know exactly what's going to happen, and it's hard to make predictions. Okay, any questions about that? I talked about that very ambiguously without examples, but you can let me know if you want me to answer any questions on that. So if the screen goes blurry, let me know, and I'll, sorry, if the screen goes blurry, just reload. Also let me know if it doesn't restore itself. Okay, what I want to talk about are ceilings and floor prices. So we spent some time discussing market clearing. Okay, so the process by which demand and supply result in a market equilibrium. Sometimes market equilibrium is prevented, okay, and that's by government intervention, where a ceiling price is imposed to permit sellers to charge for a good, to charge a particular price for a good. When the ceiling price is below equilibrium, a shortage occurs. What's an example of a ceiling price? What's a classic example of a ceiling price? Imposed by the government. Okay, I'll just go to the next one and then I'll give you my example. There's also floor price, where a minimum price is set by government that permits sellers to charge a certain price for a good. When the floor price is above equilibrium, a surplus occurs. And what could be the problem with that? And what's an example of a floor price? The classic example of a ceiling price, milk always comes up, right? That's another one. So a classic example of a ceiling price I'm going to use is rent control. So this is where the government does not permit rents to go higher than 1. But the market equilibrium is at price 2. As a result, there's excess demand. And what could possibly be wrong with that? Oh, well, we want to make, government will argue that they want to make housing affordable. So usually people who rent are not wealthy and they're subject, they have, they might be on fixed incomes, they might be seniors, or they don't have a lot of disposable income. So it's really important, governments feel, to provide security that they won't be, the rent won't be increasing. So what, on the one hand, it's humanitarian. It also, there's an argument that long-term tenants, keeping the same tenants in by not increasing their rent is better for the community. It's better for security. Neighbors know each other, and so this can be it can add to the quality of life of tenants and the safety of the property or the area. But this does create excess demand. So what does excess demand look like? What does that mean? Who are those people who aren't getting homes? So meanwhile, some prime real estate has rent control for could have rent control for 10, 20 years. People's rent didn't go up over 20 years. However, there's people who can't even find a place because there's just not enough properties. So excess demand, there have been some studies that have argued that rent control, despite its intent to make housing affordable, pushes out a class of people and renders them homeless. Okay, so that's my example. What about floor price? What's an example of floor price? So in this case, the price charged per unit is at 3, but market equilibrium is at 2. So what's a good example? What's a government intervention for that? Well, what's a good example? So you're going to end up, as a consequence, you're going to get a surplus in supply What's a classic example? Anybody know? That with all good intentions, government does what? Forces a minimum wage. So for the hourly wage, so you can say unskilled or low-skilled labor, where you can see the quantity demanded as hours of labor. There ends up being an excess. There's some people that don't get to work. So what is this accomplishing, or what is the unintended consequence of minimum wage? So the rationale for minimum wage is that, so whereas in rent control the rationale was long-term tenants and affordable housing. And for minimum wage, it's just to keep up with inflation, right? That's usually the argument, to keep up with the cost of living. But consequence is that you have a surplus, and there's going to be unemployed individuals who would have been willing to work for a lower price, but are pushed out because there's no need for them. The market, the demand for labor is here, whereas the supply is here, leaving a surplus of supply, unemployed, or people who leave the labor force and go on social assistance. So I'm not going to get into all the controversies, but you can look it up. I mean, there's research that looks at that and tries to capture that, but economists, I mean, economists, you can find an economist that thinks differently or qualifies their answer on these points, but there's evidence to show the effects of these two results. And theoretically, we would see that as a deadweight loss. Okay, so society loses. The consumer surplus that is lost with a price ceiling is known as a deadweight loss. So we would lose that area. So that good feeling for getting, for having the market, at the market equilibrium where producers are producing at a level they're willing to provide, and consumers are willing to pay. Similarly, the deadweight loss for a price floor you see here. So I'm not going to get into it too much. This slide isn't even in the book, but I just wanted to bring it back to show you the impact on deadweight loss. And this is what economists would actually try and measure. So they estimate a supply curve, a demand curve, and then estimate the social consequences in terms of deadweight loss for society of these interventions, government interventions. And they want to minimize them, so they try and find, if it's a centralized economy, they try to set it to do the minimal damage. Okay, so that's really what I wanted to say about chapter 2, and that's that. Do you guys have any questions? So that's the simplest way, is just to help you to ground these concepts in examples. There you go. Now you can argue with your friends about rent control and minimum wage. All right, so I'm going to look at chapter 3. All right, this was optimization. So we spent some time with looking at this. Okay, the objective function. Okay, let's review the terminology. Okay. An optimization problem. So I'm in Unit 3, page 3. An optimization problem involves the specification of 3 things: the objective function to be maximized or minimized, the activities or choice variables. That's the key word there, okay? This is what you're trying to do. You're trying to determine the level of that variable. That optimizes your objective function. And you need to include any constraints that restrict the values of the choice variables. So you could be optimizing with a maximization or minimization. So maximizing, so I talked about maximizing revenue or profits versus minimizing cost. And then there's the 2 types of optimization. There's using unconstrained optimization, where there's no restriction on the level of activity. And then the constraint problem, where you introduce a restriction. So what we did there was I created a budget. I said, okay, well, you have constraints. You have a budget. You can only spend so much on your inputs to either production or your I'm trying to think anyway, to your choice variables. Let's just say it like that. Okay, so you would your activities determine the value of the objective function. So you would optimize and then go back, once you found your levels, plug them back in to figure out what is the value, the optimal value of the objective function. I did some exercises, and the ones that I showed you from the mathematical exercises were using continuous functions. So we know I gave you a function, and we solve for it. We solve for the optimization problem. In the text, however, lots of the examples are using discrete choice variables, so you get a table of values. So I hope you were able to follow those. I find those a little more tedious because, I mean, they're not hard to solve, but it's just a little more tedious than an elegant continuous function. Okay, and our results will be on the margin. Marginal analysis is what we end up realizing. Analytical techniques for solving optimization problems that involve changing the values of choice variables by small amounts to see if the objective function can be further improved. Marginal analysis is the central organizing principle of economic theory. So our goal is going to be to look for the marginal impact. So adding one more unit of our activity, how does that impact our objective function? So our objective function for optimization that we focus on is the net benefit. So that's after you consider costs, right? So we did this. We worked on a problem like this. And we want to find A star, the level of activity that maximizes the net benefit. Now, I solved some problems. I gave you some functions, and those functions could look something like this drawing here, where total benefit is a concave function, total cost is a convex function, and it creates some alternatives, different levels of activity, and which is your option? What are your options, right? What is our, these are all possible, but what's the best? Well, the difference between cost and benefit is a maximum here. Net benefit is largest here at 1,000, and you result with a level of activity of 350. On this function, you can find the total benefit and total cost and actually calculate the net benefit. So all this information has been displayed for you, but we'd like to do that in a more systematic way, and that's why we end up using calculus. Calculus will quickly help us achieve the optimization, where at this level of activity, where now this curve represents net benefit, this is the curve for net benefit, or total cost minus, total benefit minus total cost. Notice we talked about this before. It also happens to be where the slope of the net benefit curve is a 0, and that denotes a peak in our net benefit. Okay, so I could give you these two functions. You can create the net benefit and then optimize it. So that's what we actually did that together. You could also create a function of marginal benefit and marginal cost. Marginal benefit, what does it mean? It means for 1 unit change in the level of activity, total benefit changes by this amount. Okay, that's really what's happening. So a 1 unit change in A impacts total benefit by the marginal benefit. So that's what marginal benefit is. Similarly, marginal cost, 1 unit change in the level of activity changes total cost. That's known as the marginal cost. So what's done here is this chart. Now, remembering the curves, these are curves here. At each point on the curve, you have a tangent, and that tangent is the derivative, right? It's the slope of the curve at the point. So what actually happens is we are calculating as we go up this curve, the slopes are getting steeper and steeper and steeper. Total cost is increasing. The marginal cost is increasing all the way up the total cost curve. So this is a plot of all those increasing slopes. And this is similarly, but this time the slopes are decreasing for a concave function. Let me just write that down. This is concave, and this is convex. And I always remember that because this makes like a letter V, like it goes. I know it goes. It's not a V, but it's going up. And I always remember this is concave because this is like an A, like a cave. Anyway, that's how I remember these things. All right, and where marginal benefit equals marginal cost happens to be in the same, at the same place where net benefit is maximized. So this is just another way to see it. This is another way to solve the problem, right? So you can solve it equating marginal cost and marginal benefit, or maximizing net benefit. But they're going to be in the same, at the same activity level either way. So that's why you see we can solve it both ways. It's important to know those are interchangeable. Yes, I'm looking at the question, Gerardo. Yes, that's where you find net benefit. Right here. And it also happens to be where the slopes of the curves are identical. Isn't that neat? So these are the most far apart when the slopes of these curves are identical. Okay, so write all that down. Okay, so how does this work in terms of discrete, when you try and solve this, not with the calculus, but looking at your options, and you have to choose a discrete level, so whole numbers, no functions. As long as marginal benefit exceeds marginal cost, keep increasing the activity level to reach your highest benefit. So let's see, what does that mean? Let's look at back at the chart. As long as marginal benefit exceeds marginal cost, you see? Marginal benefit is in all these places, as long as it's higher than marginal cost, you should keep on increasing your activity level just to here, to where they're equal. If marginal cost is greater than marginal benefit, activity should be decreased. So if marginal cost exceeds marginal benefit, you should, you want less of that per unit. Okay, so the optimal level occurs when marginal benefit is the same as marginal cost, because that will give you the optimum. It makes sense, right? So if one more unit of the activity makes you better off, it's more, there's more benefit than cost, we'll keep going up until you see the reverse. When there's no more advantage of increasing the activity, you reduce it. And that'll settle here. So then there's these tables for discrete choices, and you have to use the same principle. So what's the principle? We keep going as long as marginal benefit is greater than marginal cost, keep going. So we compare this and this, we keep going, and then marginal benefit, but then it stops, right? So we need to produce, the goal is to produce at the highest net benefit, and that also coincides. So see, we see the answer two different ways, and I keep on repeating, but here, marginal benefit is still greater than marginal cost, so you can even produce at with more, but you don't have, if you, more units will put you in reverse, so you have to stop producing, and you notice that is also telling you where the highest net benefit is, so it works out that way. Okay, so those are discrete choices where you don't have a curve. You can't have fractions like in this curve. I could have any amount of production along this curve. So that would work for commodities like rice, where you can weigh it in fractions of a pound or kilo. Yes, marginal benefit equals marginal cost is also where you have the optimal net benefit. They're the same. So that's what worked out here. So those are the things you need to remember. This is just repeating. Increase the activity as long as marginal benefit is greater than marginal cost, but decrease if it's the reverse until you reach the optimal level of activity where net benefit is the highest. Uh-oh. What's happening? Oop, I spelled that wrong. Okay, note that there's all kinds of other costs that you might think are relevant, but they just aren't. Some costs are already paid, and you can't recover those. So those don't go into our calculations or consideration. Neither do fixed costs. We can't choose those. That's not a choice variable, right? It's just they're fixed. We have to incur those expenses. So that's not considered in our decision. And then neither is average costs, which are computed by dividing total cost by the number of units of the activity. What we really care about is the relationship between benefit and cost on the margin. This is just repeating what I'm saying. Okay, so constraint optimization. So all that I've done so far, what I showed you in the graphs was unconstrained, right? We didn't have, you could just pick the best and there was no constraint to consider. But what if you have a budget constraint? What if you can't you just can't spend you can't afford, you just have a constraint, you can't afford an activity level 350. What if that's true? Well, how would we introduce that into our problem? That's what we're going to discuss next. So constraint optimization is where a manager must choose the levels of 2 or more activities in order to optimize the total benefit subject to a constraint in the form of a budget that restricts the amount that can be spent. And I ask you here to Google Lagrangian multiplier to observe constraint optimization. So let's see if I can do that. What do we get? Now, when I illustrated how to do this, how to use it mathematically, oh, I have to say graph. You see these? So these are actually plotting out in 3 dimensions the objective function, and you see considering the inputs, oh, I can't really show it. Okay, so considering the inputs on the horizontal axis and then the objective function on the vertical axis, you can see that there's minimum and maximum. So if this was like a cost minimization, you would want to be in the center of that. You want to be in the center there, if that looks like it's going to be the lowest. Anyway, so this is what we're, you're not, maybe you're never going to do anything with the Lagrangian multiplier, but that's what it's doing. It's trying to find the minimum of that function, considering the interplay of the inputs or the choice variables. For constraint optimization, it turns out that the marginal benefit per the price of that activity now represents the additional benefit per additional dollar spent on the activity. Okay, so this is going to be what we're going to focus on now. So it's constrained by its price. So the benefit, it's like benefit over cost. Benefit over its cost. So we're turning it into a per dollar cost figure. Now, ratios of marginal benefits to prices of various activities are used to allocate a fixed number of dollars among activities. So I give you these rules, right? But the textbook gives you these rules, these properties, and it seems logical, but then I really feel there's a strength in the calculus that proves these results. But and the bottom line is you've got to know the results. Okay. If you don't like the calculus or the proofs, well, I wish you would like them, but and appreciate that. But all it's doing is showing the same result. We're always arriving at the same result. Marginal benefits must be equal. And if you have constraint, it's marginal benefit over price must be equal for all the activities, all the choice variables. So consider a situation in which there are two activities, A and B. For each unit, activity A costs $4 and activity B costs $2. The manager faces a constraint of total expenditure can't spend more than $100. Okay, for all those activities. So the manager wishes to allocate 100 between the two activities so that the combined total benefit from both is maximized. So you want to maximize considering your constraint, just like real life. So it's the same idea that as long as benefit exceeds cost, you keep on adding units. In this case, as long as the benefit per price, or marginal benefit over the price, so per dollar of the unit, as long as that's greater than the marginal benefit of the other activity per unit, you keep adding and increasing unit A. So there's still an opportunity to increase total benefit by adding another unit of A, but less of B to balance the budget. Okay, so this is where we're headed, if we can achieve that. It's important to know that decreasing marginal returns are very relevant. We all experience decreasing marginal returns in life when we just consume, right? Like the first bite of double chocolate cake is really good. The second bite, it could be equally as good, but as you keep going, the benefits decrease, right? You don't get that pleasure that you did in the initial bites you had. So similarly, as you drink several cans of Coke in succession, you get even smaller amounts of additional satisfaction. As you continue studying for an exam, each additional hour of studying increases your expected exam grade by even smaller amounts. These are these are examples of diminishing marginal returns. In general, when you have constrained optimization, you have many different activities to choose. What you're trying to do, the optimum will be where the marginal benefit per price of each of those activities is equal. This will ensure your constraint is met and that you are optimizing. So, and where does that come from? That comes from calculus. So here's an example, constraint optimization where you're minimizing cost. Consider a situation which there are two activities, A and B. For each unit, activity A costs $5 and B costs $20. The manager faces a constraint. Okay, so we're going to minimize costs, but our constraint now, we're going to flip it. So this is flip. This is cost minimization, where you're not constrained by the cost like we were with the budget constraint in the last example, but instead we're minimizing cost, and our constraint is that we want to achieve a certain level of benefit. So this is just flipping the problem, looking at minimizing costs with this benefit as a constraint, as opposed to before was maximizing benefit where cost was a constraint. I hope you can see this is the same sort of problem, but I just flipped it around. So you could have, just to conclude, actually I'll say it here. Let's just go through it. So marginal analysis is an analytical technique for solving optimization problems by changing the value of a choice variable by a small amount, that's the additional unit, to see if the objective function can be further improved. The optimal level of the activity, A star, is that which maximizes net benefit, and this happens to occur where the marginal benefit is equal to marginal cost. And then I said ignore these things. The ratio marginal benefit per price denotes the additional benefit of that activity per additional dollar spent. And this is what we did. This is for unconstrained. And this is the result of constrained. So we convert the benefit, because we're constrained by the price, we convert the benefit and we offset it by its price. So we say benefit per dollar, in other words, that's what that says. And the optimum will be achieved where the ratios are all the same for all of the inputs, for all of the activities. And that's it. Mario, that's always that way. And yeah, that's always going to be the optimum. That's always the result. Okay. I have some exercises I can do too if we get through this. I'm flying through this stuff. Okay, let's do 3 statistics. So fun. All right, so I did a review of statistics last class. Let's see what you gathered and where we can go from there, okay? If you never saw statistics before, I hope it helped. Now let's see if we can apply it here. Remember, parameters are what is the real world characteristics. In our situation, when we're looking at estimating demand and supply functions, the parameters that we're going to be interested in are the marginal impact of one, or the impact of one more unit of that factor or determinant of demand or supply. That's what our parameters are going to be. We're going to be focused on the parameters for a line. I don't know if you had a chance to finish my video on regression or in statistics where I show that. So So the coefficients in an equation that determine the exact mathematical relation among the variables. So that's if you had the population, you could have estimated it. In its absence, we estimate statistics for those parameters. And those will be the coefficients in the equation for demand, function for demand. Parameter estimation is the process of finding estimates of the numerical values of the parameters of an equation. Estimates are the statistics. Oh, I repeated myself. Estimates are the statistics. They are computed from a sample of observations. A sample is a part of the entire population. So I already said that before. Okay, so regression analysis is a statistical technique for estimating the parameters of an equation and testing for statistical significance. The dependent variable is always on the y-axis, where we are looking to explain this variable using the explanatory variable x. They're thought to cause the different variable to take that value. Now, in regression, in general, you know, you can just do a regression analysis and look for correlation or relationship, but when we talk about economics and we work with managerial economics, we're looking at dependence. Okay, and we use theory to back up what we're doing. Okay, we say, well, you know, we understand, and it's been shown that demand is impacted by these variables, and that's why we do it that way. So the example given here is sales. This is our response variable, and a factor is the advertising expenditure. So how much we spend on advertising appears to increase sales, right? So it turns out, so these dots are all the observations. They're all plotted on the scatter plot. And the issue becomes, can we estimate those observations that are plotted, advertising here and sales here, can we replace those with a line so we can make predictions? So if we're thinking about spending $7,000, what sales could we expect, for instance? But we happen to have a data point for 7,000. If we go back, here we have a data point. So this was data that was collected from either previous years, or we looked at the industry, and we were able to gather information where we saw that at $7,000 spending, on average, sales were $60,000 in the last 5 years, let's say. That's what happened. And so there it is, right here. So we don't actually have to estimate for that one. We actually know it. But we can use the one we know to determine how good this line is. It looks kind of off, right? It's not that great. Like if we had used the line to make the estimate, we would have gotten here. And we would have been off by this amount. This amount of 60,000 minus whatever this is. So how do we figure out what this is that I circled? How do we figure that out? Does anybody know? How high is that? And I'm going to fix this because I don't know why it says sample. This is the simple regression line. I guess I don't know if I call it, if it's from the notes, maybe it's called sample because it's from the sample. I have to check that, if that's, anyway, tell me, how do I find this here? Does anybody know? Well, how do how do I get this value? Yeah, I'm gonna take 5 minutes. You guys can think about that. I'm gonna double check a couple of things. Take a 5-minute break, and we'll talk about that when we get back. Okay, I'm back. Okay, so you have you realize if you're looking at this, you have everything on this page, all right? You've been given. What you've been given here is the actual least squares regression line that I talked about last time. And what you have to do is you use the line. Remember, this line was this is y hat equals a plus bx, where we say a and b are parameters, statistics meant to estimate parameters. So I could put a hat on them or not. It's a tendency not to put hats on them, but anyway. So we have a hat on it because it's not exactly a line, it's a line that represents those points. So it's not exactly a line, it's a prediction line. And we can find A from knowing B and the fact that the line must pass through the two means. I did talk about that too last time. So this line was created. I don't expect you to calculate the line. I just want you to interpret it. So this is the B and this is the A, and all I have to do is put the advertising amount in there and estimate the y hat, in other words. Okay, so this is acting like X and this is acting like y hat. I might put an S hat on it. So that's what already been done here. So you got it all right here. So that estimate is 46,000. So that's going to be about here is where it is. And you compare that to what we really got and realize that it's off. Okay, it's not perfect. There's an error there, and we have a name for that error. We call it the residual. And you can actually calculate it. And the goal of using calculus to create this line just comes out of software, or like I said, I'm not going to expect you to calculate the line, but you should be able to do it given what I taught you last time. You should be able to do it for two variables, and for more than two, I just stick with the interpretation. I don't expect you to calculate it, but in higher level courses, or maybe you've taken courses to teach you how to do that calculation using a computer. But it's very, there's a pattern to it. There's a definite pattern, and you get the hang of it if you do it enough. But as it is, we just need to learn how to interpret. That's all you got to do here. So this line was chosen or determined in such a way that the errors, the residuals, are minimized. It floats in between these points so that the distance here is offset perfectly by the distance here. Okay, so we call it least squares residual because the distances are what we care about, not the sign, because the residuals above the line will all be positives. And the residuals below the line would be negatives if we just tried to minimize the total residuals. That's a bad idea because summing them would just make, would be one big zero. So we have to square the residuals and then minimize, and that's what's achieved in the calculus that results in this equation. Okay, that's where it comes from. So there it is. So what does it say? It says, How do we interpret this? Let me see if somebody could tell me. Interpret for me the 4.9719. What's the interpretation? And then interpret for me what is 11. Okay, I'm just going to round them. Don't make them. Just round this to 5. So B is 5, and A is about, well, it's 11,000, so I'll write down 11,573. And this should be dollars too. Okay, let's see who can interpret for me. So I really prefer that you read the text, that you try the exercises, that you struggle, and then I just do the review because it's more meaningful. Otherwise, when I'm talking, it's all a blur. But if you've gotten your hands dirty working with this material, then you can have some insight. That's what I really hope for. Anybody? No one's going to interpret B or A for me? Okay, so just put it in terms that, thank you, Mario, very good, but put it in the terms of the problem. Yeah, but what does it mean? Put it in a meaningful way. Like Mario was close. In a meaningful way. In terms of this problem. Struggle a little bit. Now, see, statistics is one thing, but the applications is everything. This is all we do, all that we learn all that statistics just so we can use it. It's a tool. Now let's apply it. What does it mean? Okay, you guys still are not interpreting. Okay, let me do this for you. Okay, I'm gonna do this for you. You're gonna see how easy this is. So, let me move over here. Let's do A. A equals 11,573 means when $0, or there's no, I'll make it even more. When there is no spending on advertising, who wants to finish the sentence? Sales are $11,573. So obviously other things are impacting sales, not just advertising, right? There's other determinants. So that's what that says. And B equals 4.9719 means for each dollar spent on advertising, sales increase by, how do you finish that statement? I want you guys are giving me qualitative answers. That's the best way to describe what you're giving me. I want concrete answers here. You have the numbers. You can give me quantitative answers. So that's actually $1 as well, okay? These are both dollars. These are dollars. Dollars. Let me make them better. So finish that sentence for me. For each dollar spent on advertising, sales increase by $4.97. That's right. Got it? So you guys kind of knew that, or you knew it, you didn't know how to write it. You need to know how to write this stuff now. I mean, you need to know how to write this. So there you go. Now you guys can do it. Take a screenshot. So we'll call that the sample regression line or the simple regression line. They use sample because it's a sample of data that was used. If you want, you can take a screenshot because I'm going to go on. So simple linear regression, there's a true regression line. If you had all the population data, if you had all the possible observations on sales and advertising dollars spent, for instance, you could create a regression line. It's still going to be a scatter plot that you're estimating a line for, but you would have all of the data. So you would have a scatter plot, X and Y, and still all this stuff here, and the line through it. But the difference is I have the population. So this would be an expression of the parameters. Notice I have E here. So I'm adding that in for each observation, the little I here. This is error because to reach all of these observations, I can go on the line, but then I have to go a distance, and that's what the E is. Okay, so it's called E when I make the true regression line, which I can't make because I don't have the population data, but this is what we try and estimate. This is what our goal is. And in fact, there will be an actual error if we had all the real information. So just to review, the intercept gives the value of y where the line crosses the the y-axis. The slope tells you the marginal effect, the derivative. Okay? And the random error denotes that because not all points fall on the line, you need that adjustment, that little e. Sometimes e will be 0. Sometimes points will fall on the line. Maybe, right? So, whatever. So you never really have to see that again, but that's in the background. That's what we're estimating. That's what our goal is. So that's why I kept saying, if I'm going to use A here, then the thing I estimate must be A hat. Okay, so A would be estimated with A hat and B with B hat, but I ended up just using A and B. So this is important to say. The random error term is unobservable. We don't see that. It's added to a regression model to capture the effects of all the minor unpredictable factors that affect Y, but cannot reasonably be included as explanatory variables. So what I'm saying there is, let's say I mentioned to you, it's not just advertising that is influencing sales, right? There's other factors. So let's say I even included those. I put more variables in here. The truth is there's still going to be an error. Like, it's going to be hard to perfectly predict Y with the line. It's going to be hard to predict sales on a line. There's going to be other things in fact affecting the variable. X is chosen as the explanatory variable because it does a good job of explaining the variation in X. In some instances in econometrics, we interpret X as causing Y. Okay, so, I mentioned the classical linear model, and don't worry about that too much. I just threw it in there. And what we're doing here is we are estimating the regression line such that the average or expected value of Y for each level of X is obtained. Note that the underlying relationship between Y and X is unknown, but we try and discover it by analyzing the sample data. We do not data mine, if you've heard the term. What we do is we start with theory, okay? In econometrics, you always have to prop up what you're doing with theory. So my first degree was statistics, and we did a lot of data mining. Just get data and just explore it. And I didn't feel comfortable doing that, actually. I thought I want to pick a specialized area and be an expert in that area and then use statistics as a tool. So I guess that's why I often stress that. You know, statistics is just a tool. It's used without the theory a priori. You can find all kinds of spurious correlations, they say. You know, relationships that have nothing to do with each other. There's actually a website with a bunch of those floating around. Weird things that correlate together. And there's so much data right now because of the internet, a lot of data collected. You can find correlations between obscure things. But you need to have a theory to go by before you start building models. There's different kinds of data. You might have time series data. So the one that I gave you, which one is it? Is it time series, cross-sectional, or panel? So if we look at advertising, what did we have there? We had, let's just go look at it. What kind of data is that? Is that time series? Cross-sectional? Panel? Now it matters, your data matters because it determines what statistical approaches you use. Anybody know? So look, this was a snapshot in time. For several firms. So this was determined by observing several firms in the industry all at the same time, over the same time period. I didn't write the time period anywhere, but it's assumed it's around the same time period. Either these are averages over 5 years, or they're just amounts all at once. So 1 year, the same year, so I can compare them over the firms. So this is cross-sectional. But you could also have time series data. You could say it's the same firm, but year 1, year 2, year 3. If you had data like that, it would be time series. If you had data like this for year 1, data like this for year 2, data like this for year 3, then it would be called panel data. Okay? Okay, so we're using the method of least squares. It's a method of estimating the parameters of a linear regression equation by finding the line that minimizes the sum of the squared distances from each sample data point to the sample regression line. And it uses several assumptions that I'm not going to get into right now. But the fit involves minimizing the sum of the squared residuals, where residuals are defined like I showed you before. Residuals are y observed minus predicted. I always tell students residual equals y observed minus y predicted. And the way I always remember that is in statistics, we use alphabetical order for so many things. So I always remember O before P. So we always subtract them, observed minus predicted. And if you go back to what we saw here, that's what we did. Residual would be, because I told you positive residuals on the top, that's because the observed are above the predicted line. That will always be positive. And the ones below will be negative because the observed would be below the line minus the predicted would always be a negative. What happened to this slide? Oh, okay. I already said that. And here I use the hats, right? To remind you that we're just estimating that true regression equation. And it's solved for one, if you remember, when it's just two variables, when it's x and y, the solution looks like this. You could actually reduce it to see that it ends up being, so mathematically, you don't have to prove this to me, but it'll end up being RSY over SX, and that reduces to this, which is just covariance over variance. So it measures a measure of sensitivity, the effect of X on Y. So how they covary divided for every unit, for, standardized, in other words, by X. Okay. Now, A and B do not generally equal the true values of A and B, right? They're just estimates. Now, this is the new stuff. So everything there was sort of repeating. This is new. What I'm going to say next. So A and B are random variables computed using data from a random sample. The distribution of values the estimates might take is centered around the true value of the parameter. An estimator is unbiased if its average value is equal to the true value of the parameter. So in repeated samples, on average, we expect the average value to be the same as the true value. I make a note here about unbiasedness and consistency. Unbiased refers to how valid, how close to the target an estimate is. So if this is your real estimate in here, the target, now this is both these results here, the data would here be valid and reliable. It's hitting the target and hitting right within the target. Now, this is not valid. It's right off the target, right? So this is not even a valid set of data. That can happen. You don't have a valid set of data. It's not hitting here, but they're reliable because they're close together. So reliability has to do with variance, and validity has to do with biasness. So here's the extreme of neither reliable or valid. They're all scattered all over, so they're not reliable, and they're not near, really not near the target, so it's not valid. So I just stress that point. There's two things we always look at in statistics: how valid our result is, are we hitting the target, and how close we are to hitting the target, reliable or consistent. So what you're supposed to do when you conduct a regression analysis is to also conduct the diagnostic test. Before proceeding with interpretation, you would have to verify the model assumptions. Otherwise, validity and consistency are affected. The assumptions include linearity in the parameters, that sampling is random, that there's variation in the explanatory variables, that you have zero conditional mean, you have constant variance, and your error term is normally distributed. Usually people do not conduct these diagnostic tests, but in the process we're assuming that those conditions hold, okay? So you have to remember, like I really stress, that the assumptions, I mean this is economics course, it's loaded with assumptions, each model that we look at, and similarly statistics models have assumptions. Okay, so what is this all leading to? The fact is that our estimate for B is one value from one sample, but that result comes from a distribution of possible outcomes, of possible B's. So this is the relative frequency for that estimate. So you have to think in statistics, we just got one sample, but the theory, the frequentist theory that we use in statistics is that we got one, but it comes from a set of possible ones we could have had in a different sample that we could have obtained, and we think about all possible samples. So as a result of the assumptions, this is the distribution that we expect for the parameter B. The parameter that estimates B. Or the statistic that estimates the parameter B, let's say that. So what we have to do, since it could be, it could be any of these, more likely to be around here, but it could end up being really different. Really off, okay? What we need to do is test the significance of our result. Is there sufficient evidence from the sample to indicate that the true value of the coefficient is not 0? Like, do we really have something? Do we really have a slope? So for instance, if we're talking about 2, because we're looking for a relationship, right? Let's say the data is all scattered around. You kind of see, you can make a line. I can make a line and say, wow, the B is positive, so let's say B is 2. So I get a B of 2, but how good is that B? Is it really 2? Could it just as well have been something else? How well do those fit to the line? That's going to be captured in the regression coefficient. The coefficient tells us the strength and the direction of the linear relationship between x and y. So we have to conduct a hypothesis test, which is a statistical technique for making a probabilistic statement about the true value of a parameter. And what we focus on is whether there's sufficient evidence to suggest that B is not 0. So anyway, what we're going to do is disprove, right? So we set up a hypothesis. Statistics is about averages and relative measures and disproving hypotheses. So we make a hypothesis. And in regression, the hypothesis is the conservative hypothesis. It's that there is no effect. So there is no relationship. The slope is not anything. It's just 0. There's no slope. There's no trend, in other words. No trend. And we're going to test it against the alternative. So this stands for the null hypothesis. And this stands for the alternative hypothesis. And the null hypothesis is null, for nothing, no effect. So that's where we put the b equals 0. So what we're trying to say is, what our approach is, there's no effect. Make a statement that there's no effect, and then we have to look for evidence that that's wrong. So the approach is we assume B is 0. So even if B is 0, is it possible that the sample will produce an estimate B hat that is different from 0? The result let me see. What we're going to do is perform a t-test to determine this is true or not. So the t-test is set up. Just bear with me. Now I'm just doing this for 2 variables right now, but this you would be doing with regression with many variables. You would be testing all the different slopes, and the output would give you that information. So this is the hypothesis against the alternative. The alternative, so the null is no effect. And the alternative is what you believe to be true if you reject H naught. Now, I didn't teach you about hypothesis testing. It'd be great if you had that information from the before. If you don't, I think we're still okay, because this should be familiar to you. The T distribution is related to the Z distribution, right? We talked about the standard normal distribution. The standard normal distribution, remember, is normal with a mean of 0 and a standard deviation of 1. Right? And being normal, it has those properties. The properties 68, 95, 99.7. Within one standard deviation of the mean are 68% of the observations. Within 2 standard deviations of the mean, there's 95% of the observations. And within 3 standard deviations, 99.7% of the observations. The T distribution allows for more outliers. It has a different distribution depending on how many, it's related actually to a sample, okay? It's related to how many observations in the sample. Okay, I have to go turn off that oven, hold on. Give me a minute. Okay, I'm back, sorry. All right, so the normal distribution is like that. That's the standard normal. And the T distribution is more like, oops. It has like, it's flatter. I can't do it nicely. Something like that. It's flatter for, you know, n minus 1. So for degrees of freedom, where degrees of freedom determine the peakedness of it. When n is about 100, no, it's more like 1,000. When you have about 1,000 observations, the normal and the standard normal, sorry, the T distribution looks like the standard normal distribution. I think it's 1,000. I have to double check. Yeah, I have it like at 1,000. Okay, so So anyway, the point is it's still symmetric. The t-distribution that this thing comes from it's symmetric, and it looks like for larger observations, it looks like the standard normal, larger amount of observations. But anyway, you don't have to worry, you don't have to look on any tables or anything, because the results will just be given to you. The t ratio is computed as this. What is this? Can anybody tell me, explain to me what we're looking at here? No idea, right? Okay. What we do is get a sample, and we calculate we have a sample of pairs of observations, right? And we're looking for a relationship, and we calculate the least squares regression line with a b. And what we're going to do is test how if we assume that there is no effect, that's how we're going to start. And we're going to disprove that there's no effect and conclude there's an effect. So we begin with an assumption, because we can't really do anything without making an assumption. So we assume H naught is true, that there is no trend between X and Y. B is 0. Then with our sample, we go get our sample and we get B. So we estimate B. So this is our estimate of B. And then we check how different is B from 0. Is it the same or different than 0? How will we figure that out in statistics? How do we compare numbers in statistics? Numbers that have a distribution. B has a distribution. It has a distribution, and when I standardize that distribution, that looks really weird for you, right? Let me write that. Let me do this a different way. If I take, remember when we standardize to create Z, we would do X minus mu over sigma, right? That's how we standardize. So in general, to standardize, I'm going to write in general. Are you still with me? Stay with me. To standardize, we're going to get, in this case, we're going to get a t distribution, not a z, a t statistic. I'll talk about that in a bit. And we take our value of b hat and we minus its mean, and we divide by its standard, we call it standard error, but it's like a standard deviation. So we standardize. What's the mean? Well, all we know is what we assume to be true at this point. So we assume that the average value of b was 0. So we're actually minusing 0 here. And then we're dividing by the standard deviation. We call it standard error instead of standard deviation because we use an estimate of the standard deviation to divide. So it's just like a standard deviation. So this is all given to you, but that's where they got it from. So they take your value, so this is a statistic, right? And then they standardize this statistic to create another statistic. So this is another statistic. This is also a statistic, right? Because it's a number you calculate from a sample. So the B hat is a statistic that you get from your sample. You standardize and get another statistic called T. All values computed from your sample. And what you're going to do is figure out, in standard deviations from the mean, how far are you away from the mean? So this number gets converted to standard deviations from the mean. And then you have to sort out if it's too far away. If you assumed that there was no trend, you assumed the mean was 0. You assumed that the estimate was 0. But you got a number very far away from 0. So what you would find is that you are in the outliers. Your result is an outlier. It's very strange. And if it's strange enough, it's enough evidence to say this assumption is wrong. That is disproving a hypothesis. As a result, we would reject the hypothesis, the null hypothesis, and say that B is not 0. All of this just to preserve our result and say there is a trend. It's not a bad result. It's not a meaningless result. Okay, so all these details, you don't have to worry too much. We just go to the output. Let's go to the output. Wait, I have to tell you about p-values. Oh, so much to tell you. Okay, here's the result. Let me tell you about p-values before I do all this. You really don't need all this detail, but it's actually minimal what they give you. So as I said, what we're going to do, just to repeat, if you're still with me, I'm going to take the result and I'm going to standardize it. Standardizing it, what was its average? What should it have been on average? I'm going to minus it, and then I'm going to divide by the standard deviation, the estimate of the standard deviation called the standard error, and get this. And this represents how many standard deviations I am away from the assumed or hypothesized mean. Now, what did we say? Let's see if we can remember. Can you even read that? Let me do that again. Now, when is a result an outlier? If data is symmetric. What did we say? An observation is an outlier if the data is symmetric. What did we say? Nobody? So remember, if an observation, even if it's a symmetric distribution, if an observation is more than 3 standard deviations from the mean, we usually say that's an outlier, right? So every distribution has specifications of what's an outlier. And when it comes to the t-distribution, or any distribution, what we do, because distributions are different, we estimate the chance, actually we estimate rather than, let's see. So outlier, right, would be far away from the rest of the data, and what we need to do is we need to focus on the tail. So we convert the number of standard deviations from the mean into the tail probability. That's what we do. And when we do that, we create a p-value. That's what we're doing. Right, so Gerardo said yes. We were talking about outside 3 standard deviations from the mean would be an outlier. But from distribution to distribution, there's kind of like different rules, and the rules all have to do with the fact are related to the tail probability. So we convert the distance from the mean into the probability associated with being over here, you know, in the tail. So how do we do that? Okay, let me just review this quickly. So SB is the standard error of the estimate B hat, so that's like a standard deviation. You need to use the t-table to choose the critical value of t. Okay, so there's 2 ways to look at this to figure out if your result is an outlier. That's our goal here. Is the result too far away from the mean? Is it too many standard deviations away, or is it in the tail? There's 2 ways to look at that. One is to figure out the threshold, the cutoff for being too far away. So a critical value would be that threshold. So if I found out what this was and this, the thresholds for cutoff where the outliers start, that's known as a critical value. Okay, those are critical values. Those blues. Now, if 0 is in the middle, okay, those are going to be symmetric. They're going to be balanced. One will be a positive, one will be a negative. And when we talk about t-distributions, the degrees of freedom for picking a critical value with many parameters, this k has to do with the number of parameters. If you just use one, so what am I talking about? How many parameters is talking about your equation? If you have y equals a plus b, x plus c, oops, I didn't do c, plus cz plus d, no, I'm going to stop there. Okay, so this one has how many parameters here? Am I trying to estimate? How many parameters am I estimating? many parameters am I estimating? Nobody knows. Well, we're going to estimate A, B, and C. So that's 3. So K would be 3, and N would be the number of observations. And that would help you determine the threshold. Now, I'm just telling you that because the text, the cases will give you those values, and you won't know where they come from. I'm just checking in the back of the book if you have tables. I think you have tables. Or you can get these in Excel. You can get these results in Excel if you're interested. No tables. So they're just gonna, oh yeah, there's tables. There's table for F and minus K, okay. Very good. Okay, don't forget the A, guys. Don't forget the intercept. That's a parameter too. All right. So we need to perform this t-test to determine if our slope is meaningful, if there's really a trend. So the approach is, if the absolute value of the t-statistic, which was the number of degrees of freedom, sorry, the number of standard deviations from the mean, is greater than the critical value t, the parameter estimate is said to be statistically significant at the given level of significance. So this threshold will depend on N and K, and then you just compare, you just see if you're outside of it, right? If you're here, then you're an outlier. So what you're doing is checking to see if it's greater than the critical value, either higher or lower. That's why they say absolute values. And then the parameter estimate would be statistically significant. It means, what does statistically significant mean? It means you would reject H naught and say B is not equal to 0. B demonstrates a trend. So statistically significant means you found something special. You found a trend. You found a pattern. All based on the fact that you made the assumption at the beginning that there was none. No trend, no relationship, versus yes, there's a relationship. And now you do that for all the parameters. So this is one approach using the critical values. This will just be, you'd have to go to a table, or what happens in the output is rather than the critical value, as I explained, they calculate the p-value associated with the t that you calculated. So let me see. P-value. The p-value, I'm just going to draw a picture. So basically, either I can use the critical value here that I found in a chart that tells me where the outliers start. And I check if my t stat, I'm going to make it a red, is out there. If so, out here, if it's there, I reject the null hypothesis and I say I found a relationship. Or if it's out here, I reject the null hypothesis. Here and here, I say fail to reject. And the way you would conclude is there is that there's no evidence to suggest that B has a trend, that there's a trend. So that's one way to do it that I discussed. That's the critical value way. And you'll see the text will mention critical values, and that's what it's doing. It's testing your t statistic that you computed. The other way is using the p-values. What the p-value is, it focuses on the t-stat and calculates another statistic called the p-value. The p-value is the probability of being as extreme or more extreme than the test statistic, assuming the null hypothesis. So to draw this, to get this blue curve, I assumed H naught is true, and I proceeded, I used my test. So I conducted my, I drew my sample, and then I calculated the slope, and then I figured out how many standard deviations I'm away from the hypothesized no slope result, and I ended up here. And this p-value is the probability of being here, assuming the slope was 0. So this should be small, right? Because I'm out in the tail. I need to be past this critical value that says it's an outlier. Outliers are out here, so this should be small. In other words, it should be small to reject H naught. Let me put that over here. It should be small. What does that mean? What is it saying? It's saying that the probability of getting this result was so small, the result is so strange, it was an outlier, and for that reason, there's something wrong. Assuming there's nothing wrong with my sample, okay, we're going to have to assume that, there must be something wrong with what we did at the beginning. The assumption was wrong, and that's why we throw out the assumption. Okay, so what you're going to look for is a p-value that is small. Smaller than what we call the level of significance, and that's usually set to be about 5%. So if it's smaller than a 5% chance of seeing that result, then this implies that the test is significant, you did get something, you did find a trend, reject the null hypothesis. The coefficient is different from 0. So we call it the coefficient, the slope, the parameter. Those are interchangeable terms. I don't like calling it a parameter because it's an estimate of a parameter. Okay, so what did I say here? The chance of getting that value was smaller than expected, but we still got it. Something's wrong with the assumption that the coefficient actually is 0, so we reject the assumption. And so what are we rejecting again for people who are still trying to grasp this? We're rejecting this assumption that B was 0. So that is disproving the hypothesis. Now a p-value for a two-sided test, I should tell you, just in case it comes up, is testing both sides to be an outlier. So it's, the p-value is the total of this and this over here. All right. So you guys can review that video. I still have some time. I want to look at the output and then we'll talk about R and all this other stuff. Okay, so here's some output. Again, we have R&D and price to earnings ratio. What is the relationship? Is there a relationship? So you see, there's a scatter all about, and you know, I'm confidently draw a line. The line is a result of statistical output where it conducted a least squares regression analysis for two variables, two parameters, and it floats these positive residuals between these positive residuals and these negative ones, just perfectly floating through the middle. So there it is. Here's the regression line. We can interpret the slope and the intercept. But how meaningful is this? So here's the output. So let's see. Here's the intercept. It was 6. That was the estimate of the parameter. It gives you the standard error, so that's like the estimate of the standard deviation. It already calculated the t ratio for you, so that's giving you this thing. So it's already done for you. The standardized value, right? So this is saying this is 7 standard deviations from 0. That seems quite far, doesn't it? And this one is, okay, so what's this? This is the variable, R&D, I guess. And it was 0.74. This was the standard. Okay, so it's 4.48 standard deviations from the mean. So that's far too. So these are far away. So the probabilities of being out there are very small. Both of these are smaller than 5%. So you reject the null. That's how you conclude. Let me do this bigger. So this is where you conclude. Now, we didn't have to go, the only reason I mentioned about the critical values is because I know it's in the textbook and they talk about critical values and they compare these to critical values. So one approach is compare to critical values or just look at the p-value. They give you both output here. So you have to make the interpretation, since this is less than 5%, you reject the null hypothesis, and this is less than 5%, you reject the null hypothesis. So the test is significant. We say the test is significant, and the estimates that we got are meaningful. So the result of a slope, the intercept was 6, and the slope, oh my goodness, the intercept was 6, that was the coefficient, and the slope was 0.74. So that's how you read these things. The other thing on here, they give you what's called an R square. So the observations are here. This is n. We know because of this that k is equal to 2, right? There's R square, F ratio, and p-value. Let's see what those are. Any questions so far? You guys getting a better idea what to do? if you haven't already figured it out. So what's R square? R square is interpreted as the fraction of total variation in the dependent variable y that is explained by the variation in x. In simple regression, when you just have two variables, that's how we would interpret that. A high R squared, so for instance, so R squared is basically R squared. R squared is just taking R squared that we talked about last class, right? Well, in the review. R was an index, remember, between 0 and 1. Did I say 0 and 1? Negative 1 and 1, sorry. Negative 1 and 1. Sometimes I don't realize what I'm saying. R is between negative 1 and 1. It's an index. But when we square it, it becomes a percentage. Okay, wait, questions? Yes, Mario. Okay, so I'm going to go back before I continue with this. Let me go back to this. So the coefficients are the coefficient, they're both coefficients. These are both coefficients, but this is the intercept. There's just different names for it, right? This is the intercept and this is the slope of that line. Okay, what's the other question? Yeah, Gerardo's asking, do they have to be less than 5? Unless otherwise stated, we usually use 5% to reject. We're comfortable with 5%. Now, you can imagine if you're very conservative and you don't want to reject, you make this smaller and smaller and smaller, right? So it's kind of subjective in that way. But the standard, the convention in statistics is to use 5% to reject. What do you mean, Gerardo? What about only one? I'm not sure what your question is. Okay, I'm going to continue. So it went from an index to a percentage. It goes from an index to a percentage, a fraction of total variation. So it goes from an index, let me make a note. It's a percentage. 0 to 100%. So a high percentage would mean that they're highly correlated. It doesn't necessarily prove that X causes Y. You would use theory to support you in saying something like that, or you would conduct an experiment to prove it. But just observational data, you can't say this causes that, right? You have to have theory to back you up. Okay, so that's the R square. So let's see, what was the R square? So it says 53% of the variation in y is explained by x. That's what it says over here, right? Let's go back. Coefficient of determination measures the fraction of total variation in the dependent variable that is explained by the variation in x. Okay, so that's what it is. So I don't know, is that high? There are some rules of thumb. I think I mentioned to you for simple regression. Let's do the test. This was n was 20, right? Let's see if it's. So this says 53% of the variation in y. What was y again? It was price to earnings ratio. Was explained by R&D. I say R&D's variation, but no, I'll just leave it like that. By the variation in R&D. Okay, so they moved does one predict another? Is it explaining it 53%? How do I know? Remember I showed you if R is greater than n, what was it, n over, no, it wasn't that. It was 2 over square root of n. I think I showed you that. So if R is greater than or equal to 2 over square root of n, we can say there's a relationship. Probably, let's see, with 20. So n is 20. What is that? So 20. Okay, so this turns out to be so as long as R is, sorry, not 45%, sorry, is greater than 0.45, I didn't do that right. If R is greater than 0.45 or negative R is less than negative 0.45, that's what that means. If it's a negative. So if it's R is greater than 0.45 or R is less than negative 0.45, you would say there is a relationship. But where's the R? How do we find the R? Anybody know? I have R squared. So I have R squared. What I can do is to find the R of this relationship without any other calculations. Well, I mean, I have to make a calculate, but without any other data, I can make an R calculation by taking the square root of R squared. And this turns out to be 0.73. So our R for our data is 0.73. All we needed was 0.45, so it looks like we're okay. Okay, got it? If it was negative, you would have to put a negative in front of here and compare it to the negative, but you get the point, I hope. So this means that it's a good fit. We got good fit, we got trend. Okay, we got a trend that's meaningful, that's not zero, and we got a good fit. So that's saying the slope is significant and the fit isn't so bad. Right, well actually let's go back to the graph. So that's what it's showing. So the fit is good. And the slope is significant. And the intercept is significant. And so what's next? Oh, the F. So we really, those are the most important things. The fit means that what does the fit mean? We can use the prediction line. In other words, we can make predictions with it. So we can estimate how much, if we want price to earnings ratio, a specific one, we can invest in R&D in a certain amount as a percentage of sales. Okay, what else? The F. Oh, let me remind you, this is for simple regression, all this analysis, but it's analogous, it's similar for the others, but for two variables, X and Y, this is the approach. So where did we leave off? Okay, R squared, what about F? F test is used to test for significance of overall regression equation. Compare F statistic to critical F value from F table. So you have an F table there. You need to use n minus k and k minus 1 to identify. So what you're doing is the same sort of thing, okay? Where you're trying to find the critical value. Is your result an outlier? If so, we reject. So critical values, remember, are the threshold to rejecting a null hypothesis. In this case, what's the null hypothesis for the F test? Did I write it here? Oh, it's not even here. Okay, yeah, it's at the top. Okay, the F test is used for the overall regression equation So it tests simultaneously the null hypothesis would be that there's really no line. A equals B equals 0. There's no trend, there's no parameters. And the alternative would be at least one of those is not equal to 0. I hope it explains that. So anyway, it's the same sort of thing, same sort of result. By looking at the R and the parameters, you're getting the same sort of things. But this is a one look, and again, you can look for the critical values or just look at the p-values. Sorry, I shouldn't have done that. I remember that's if you have the critical values, you check if you need to reject, or you calculate your test statistic, or you take the test statistic. What am I doing? In this case, it's called an F statistic. And then you compute the p-value. I don't think it's drawn like that. That's not the F. The F, it looks different. I should stop drawing. Let me erase that. That's not what it looks like. F, it looks different. But the idea being the same. Where's the F? I'm just telling you analogously because you don't need to be an expert statistician, but the same idea that you can either look at the critical values or get the p-value. I'm just looking. I'm gonna pull it up here. There. So it also depends on degrees of freedom. It has a different pattern depending on the parameters and the sample size, but it slopes like that. Okay, it's not symmetric, in other words, but the same idea. I'm going to look for the critical value and see if I'm too far away, so I probably shouldn't have drawn that. So I'm just going to write like. Think of hypothesis testing. We call it hypothesis testing. But the F test is on the F with the F distribution that looks like skewed. Anyway, don't need to get into that too much. Basically, all you have to do is do the same thing where see this? That's the ratio here. Then you would have to go into a table and find the critical value, but it's faster if you just look here. And again, you use 0.05 to reject, and this means you can reject the null and that you have something here. You know, at least one of the parameters is not 0. So you with me? I hope I didn't lose you. So that's basically the full analysis. Oh, it's 9 o'clock. So that's the full analysis for the simple regression. I still have a little bit to go, and I didn't even do elasticity. So I'm going to let you guys go now. In the morning, I'll post about elasticity. If you still want some more time to work on the test, let me know. I can add some days on there, okay? I have no problem with that. I really want you to understand. Yeah, so I'll do, this is chapter 4. I have to do 5 and 6, so let's see. All I had to do, oh, multiple regression. Okay, that's not hard. I can do that too. So I'm going to do that tomorrow morning. Multiple, oh, let's see. I have to do 5. Consumer behavior. And it also results in, oh, the indifference maps thing. Okay, so I have to do this. And then elasticities. Okay. So if you still need time, let me know. I can add some days. Okay. Yes, the p-value header though is the easiest. I but the thing is the text talks about critical values, so I just wanted to mention what critical values are, but always just go to the p-values, all right? Just go to the p-values, because they are one and the same, but the p-value is easier to interpret. You don't have to look at a table or a chart. Okay, so I can give you, how many days do you guys want? Because I'll finish 4, and I guess I'll do 5 and 6 tomorrow. So I guess you guys can have till Friday if you want. Friday night or Saturday night, let me know. Otherwise, if people are gone or leaving, good night. Let me know what you think. I'll stay back a few minutes. Bye for now. Friday or Saturday. Okay, so I'll make it Saturday at midnight. Before midnight. Before the clock strikes 12. Okay, and then, yeah, I gotta post. I still gotta make you videos. All right, let's be in touch. Bye for now. Thank you. I hope it helps.